time we should get going. I'm Alan Calder, delighted to introduce student in our group, my student, William Boyd, who undergrad at Michigan State, became highly recommended from them. And we'll see why today, as he's going to talk about his dissertation research in the progenitor of a stellar explosion. Thank you, everybody, for coming.
Thank you all for showing up, and those online as well, even if you don't get pizza. So yeah, as Alan said, I'm going to be talking about exploding stars, simulating them with computers. So broadly speaking, I work with stars and computers. For this talk, I'm going to start with going over lots of the astronomy aspects of this. So kind of how are we going to get to this supernovae? How do you actually blow up a star? What even is a star? I'm gonna assume most of you don't have much background in astronomy, but that's okay. So after that, I'm gonna start talking about more of the simulations and kind of specifically what sort of simulations I do and some of the aspects that go into them, the different computational challenges and kind of physics that make this so interesting and challenging at the same time. And then finally, I'm going to talk a little bit more about kind of cutting edge science, I guess, that we're actually using these simulations for. So to start off, what is a star? So we should all know about one star, that's the sun. It's burning hydrogen. It's kind of in the main stage of a star's life. And these stars you can really think of as just being large, stable fusion machines. So they're just fusing elements in the middle that's creating energy. That energy is what keeps these from collapsing. So gravity is constantly trying to pull stars into just a little black hole, I guess. But it's the kind of fusion and burning that keeps these out. So a brief kind of oversimplification of a star's life. We start with the sun. It's kind of just burning hydrogen. That's what happens most of the time. But eventually we're going to run out of hydrogen. So what we end up is after we're out of hydrogen, we have helium. And we have this red giant phase where for the most part, it's burning helium, again, keeping it away from collapse. But some funky stuff does go on there. Then finally, after we run out of helium, we end up with what's called a white dwarf. So this little guy right here that the arrow is pointing at, that's the white dwarf, right next to a regular star. So these things are much, much smaller than your standard other stars in this lifetime kind of sequence. And they don't actually do any fusion or burning of anything. So we'll talk more about what keeps them from holding up in gravity. Other thing that I'm interested in work on a lot is just type 1a supernovae. So what that means is just a thermonuclear explosion out in space. And what thermonuclear explosions means is just some sort of explosion caused by nuclear reactions. These things are very, very bright. So in this picture, we have a galaxy right here made up of billions of stars. And right next to it is supernovae going off. These are about the same brightness. So supernovae is on the order of billions of starlight added up together. So these are tremendously bright. This makes them very useful for lots of areas of astronomy. And there's some other aspects that make them useful as well. And we don't really know what they are. So observations and kind of theory suggest that this is a white dwarf that's blowing up. So let's look back at what kind of goes into a white dwarf. I already said that this is like kind of the end of the life for a sun-like star. It's made up of carbon and oxygen. That's what you get after all the hydrogen and helium burning. Mostly just carbon and oxygen. And there's no more fusion or burning that is kind of holding it up. And instead, it has to do with what we call electron degeneracy pressure. So this material is packed in so tightly that the kind of physics of electrons is playing a role. Electrons don't like being too close together. And so they exert this pressure outward that keeps this white dwarf up. And this all has to do with them being very, very dense. We have about the mass of the sun packed into about the size of the Earth. And on its own, it just kind of cools down. There's no kind of dynamic process. There's no fusion going on, no burning. So how the heck can this explode? Maybe we need two stars. One's not going to do it. Why don't we just add another one in? And luckily, many stars are found in these kind of binary pairs. Roughly half of the stars in our galaxy, we believe now, are in these multi-star systems. And often they'll look like this. They're orbiting each other, but they're not really interacting too much. But if they get close enough, they can actually start transferring mass in between each other. And if they're even closer, they might even collide and merge. So this seems like a reasonable pathway where maybe we can get something to explode out of this. So astronomers have thought up lots of ideas. They're very good at brainstorming. And this is a flow chart of many different pathways where we could get a star to explode. So as you can see, we have no idea what we're doing. But that's okay. This is still a very active area of research. We have lots of ideas. We're still trying to test them and figure them out. But to kind of break this problem into two parts, we can first think of what is the system that this is coming from. We call this the progenitor system. So we have one white dwarf, we're pretty sure about that. But is it orbiting around another kind of sun-like star, a more massive star, like one of those red giants? Is it two white dwarfs orbiting around each other? Or maybe even something more exotic? And just because we have this kind of system of two stars orbiting, we still have to blow them up somehow. So what's the kind of ignition mechanism that we could look at? So I'm going to show a few different examples of ignition mechanisms, really cool simulations, I think. And we're going to start off with what's usually called the double detonation. So what we're looking at here is a slice through a white dwarf, and we're looking at a few different parameters. The main one that we're gonna focus on is this left side, the temperature plot, and also the right side, which is a plot that's kind of showing the pressure waves. You'll see how that's important in a little bit. But we start off with just kind of on the outside of the white dwarf here. We're gonna have a hot spot that's going to ignite the kind of atmosphere, kind of thin material around the white dwarf. And it's going to move all the way around, heating that whole area up. Now that's the first detonation. Now, if I pause here, you can see this kind of gray pressure wave that's been induced from this first detonation is now traveling inward to the center of the star. And it's going to go kind of slowly, but eventually it's going to hit the center. And on the left, you'll see a big explosion. Now that's the main kind of type 1A supernova that we'll see that just incinerates the whole star. So maybe we don't even have one explosion. We have two explosions to get this thing to work. Another idea is these two white dwarfs, if we have two white dwarfs, maybe they can collide and merge together, and that can set off an explosion. And so people have looked at that as well. So this is a simulation. Again, now we have two white dwarfs. One's a bit more massive than the other, and they're gonna rotate together and start kind of merging until they combine into one single white dwarf with a very kind of messy sort of accretion disk all around it. Finally, this is kind of maybe the most simple explanation. We just have some sort of nuclear runaway that starts in the center of the white dwarf. So this blue region on the outside, this is kind of showing the surface of the white dwarf. And we're gonna have this hot spot in the middle that sets off this thermonuclear explosion. We're gonna jet out. And it's gonna kind of hit the surface and really start to expand all around the star. It's a little scary, but also fascinating. So I've just shown three kind of pretty different ways we could actually blow up a white dwarf. But I haven't actually explained how we get to these scenarios. We started with 2 stars. How are we going to get from 2 stars to something like this? And so the idea, I'm going to kind of focus and narrow in on one idea, one kind of explanation, which is that last one where we have some sort of hot spot in the center of the white dwarf, and that's going to cause it to explode. And so from this sort of picture, the key to all of it is that the white dwarf is gaining mass. Mass is getting deposited onto this white dwarf. And as this white dwarf becomes more massive, it's also going to get hotter and denser in the very center of the core. And eventually, if the temperature gets high enough, we can start burning carbon. And the beginning of this burning isn't actually going to be our explosion. For a while, this is just going to be kind of relatively small amounts of burning. We call this sort of simmering phase. And all that this is going to do is start to drive convection in the center. So a lot like if you just put a pot of water on a burner, it's going to start causing all the water to move around and you get some sort of kind of boiling thing happening here. So this is going to go on for about 1,000 to 10,000 years. And then eventually, because this white dwarf is still gaining mass through all this, it's still getting hotter and hotter. We can expect that it will go into this big thermonuclear runaway. But this kind of simmering phase, this is what I'm most interested in. I want to make sure we understand what's going on in this like 1,000 to 10,000 years, and can we eventually find some evidence that the white dwarf had to go through a simmering phase that would kind of rule out maybe different sort of avenues for how to get these type of things. So to go into more detail, I want to unpeel some of the layers that go into all these fancy simulations, these fluid simulations, look at the kind of challenges, both physical and computational, and maybe even look at some of the mistakes I made early on, some of the simulations I tried to run. But to start off, I'll actually just show you the simulation, because that's the best part of all these talks. There we go. So this is a simulation.
Bulk of the cluster material, nearly 90% by.
So this is a simulation of looking at the convection in the white dwarf on its way to exploding. And what we're really doing is we're like kind of peeking into the very middle. So looking at just the core region of this white dwarf. And what we're seeing is all sorts of kind of mixing of material, kind of churning around. And I'll get into what sort of material we care about and what we're looking at in more detail later. But for right now, the kind of main takeaway is that it looks kind of cool. So how do we actually make one of these things work? So what we're doing is we're modeling fluids. So white dwarfs are just like water or air, all the same things, all just fluids kind of moving around. And the way that we kind of try and simulate this is called the finite volume method. So we're going to divide up our sort of simulation domain into a bunch of little cells. This is kind of an exaggeration. They're much smaller than this, but In each of these little cells, we're going to keep track of all the different properties like density or temperature, velocity, what sort of material is in each cell. We care about how much carbon or oxygen is in there. And then we're going to try and predict the future. And we do this basically by applying conservation laws. So these laws are going to tell us how these individual cells interact with each other and how material will flow back and forth between these cells. And these laws are just mass, momentum, and energy, kind of the fundamental things in physics that they're not going to disappear. We have to keep track of them one way or another. So I'm going to kind of go into detail into one aspect of this, and that's kind of how we advance in time. So we would love to just start with our initial state, predict the end of the simulation in just one time step. But unfortunately, that doesn't work. Instead, we have to take really small, kind of tiny time steps. And that's because when we are predicting with these sort of conservation laws, we don't want to move any fluid more than one kind of cell at a time. So if we start with a cell has some velocity of like 2 cell widths, we don't want to take a time step more than half a second. Because you can't just like kind of jump over your neighbor. Otherwise, everything will just be unstable and we'll get garbage out of it. So the reason that we can't predict the future as far as we want to really has to do with how fast the fluid is moving. But that's not the whole picture. So we have to really think about how is the information moving in a fluid. So one way is through these fluid motions, as I just kind of explained. If you're sitting in front of a fan, you will feel the air blowing into you. That's kind of all the information you need to know that there's a fan there. But if you're on the other side of the room, you might still be able to hear the fan, even if you don't feel the air blowing. That's coming from the kind of sound waves or the acoustic waves. So these also carry information. And so the speed of sound can also limit how quickly or how far in advance we can predict and kind of limit the time step. So all fluids have a different sound speed, depending on properties like pressure, density, and such. And if the sound speed is too high, it can actually cause pretty significant problems. So the kind of, what's this, the Mach number? Yes. So we define a Mach number, and that's just the fluid speed divided by the speed of sound. And this kind of tells us a little bit about the relation between those in our simulations. So if we're in a low Mach regime, that means the speed of sound is much faster than the fluid speed, and so it's going to limit our time step. Now, in this kind of whiteboard convection scenario, if you remember that simulation I was showing, everything was moving kind of slowly. And so we are in a low Mach regime. The white dwarf has a very high sound speed in it. Everything's kind of packed in together and can communicate quickly. And so we have a Mach number of 10 to the minus 3. That means the kind of time step that we want to take is 1,000 times smaller or larger. We have to go 1,000 times slower than we otherwise would want to. So that actually makes these simulations unfeasible to do with computers. It's not just going to take 1,000 times the resources, which is already kind of absurd, but in fact, because we'll have to take 1,000 times more time steps, we'll be kind of accruing different ground off errors and other kind of machine precision type things. And it's just going to erase any sort of physical knowledge that we can get from these simulations. So we need some way around this to get rid of these sound waves. And luckily, we have a way. So the code that I use is called Maestro X, and it's a low Mach hydrodynamic code. And that means that it's solving kind of slightly altered equations than more standard compressible code does. And what this effectively does is filter out the sound waves. These sound waves luckily don't carry much information. So as long as we are careful about how we filter them out, we're not actually losing any of the physics in the simulation. But we get to have a big kind of time boost because now we're not time step limited by the sound waves, but instead we're time step limited by the fluid motions themselves. So we can really track these fluids in the way that we want to. The one kind of drawback is this doesn't work for anything moving too quickly. Luckily, we don't have to worry about that, but in some contexts, that would cause an issue. And then the kind of bedrock of Maestro X is this AMRX. So this is kind of the software framework that it works on. AMRX handles kind of the mesh cell kind of data structures that we rely on, and it holds the sort of linear solvers to do all the solving of the differential equations and things like that. And it's massively kind of parallelized with a sort of MPI plus whatever you want on top of it, GPUs or OpenMP. So it's really flexible, and there's lots of different sort of hydrodynamic codes that are built on this framework, both in astronomy and other scientific domains. Okay, so now I'm going to talk about some of the struggles with using low Mach codes and using hydrodynamics in general. So in this example, we have to start our simulations with something. We can't just have nothing there. Luckily, there's lots of kind of one-dimensional models that look at a star and say, well, you're kind of spherical. Let's just collapse you down into one line in radius. And so we can use these as a starting spot for our simulations. So we'll have something like a density profile that's changing with radius, and we can just kind of map it onto our 3D grid, which is kind of Cartesian based. And we do this with some kind of interpolation scheme. And as long as we're careful, there's no issues at all. But if we're not super careful, we end up with some kind of small errors in some places. So this is looking at the kind of difference between the density we expect and the density that we mapped onto our grid. And so most places it's 0, but we have this kind of outer ring with really small errors. This is a relative error of 10 to the minus 7. So this shouldn't cause any issues. If we advance in time a little bit, now we have a few rings moving out. So that's not great, but we're still at a relative error of like 10 to the minus 4. Maybe this still won't cause any issues. Oh, now we have weird plume things coming in from all the cardinal directions. This is not how convection works. Convection, you have something heated up in the middle, it moves outward and it kind of cycles around. There should be nothing falling onto our simulation. So starting from just really kind of almost negligible, or what you might think would be negligible errors, these can expand and kind of build up very quickly. This can happen in kind of any hydrodynamic code, but these low Mach codes are specifically sensitive to this because they're assuming the star is stable. Stars are very, very stable, but if we're not careful, we can kind of mess that up. So especially at the beginning of simulations and starting different simulation runs, you gotta have to be very, very careful that everything is nice and smooth. Good. The other aspect to this is kind of the computational resources that go into making these simulations. These can be quite expensive. And so the first thing I have to note is this convection is 3-dimensional, and it's inherently 3-dimensional. There's no real way to model convection in any kind of lower dimension in 2D or 1D without making these sort of approximations that just don't quite hold up. So to really solve and like look into this problem, we need to do these 3D simulations, and these get very expensive very quickly. So the simulations that I was showing have been running for now, utilize 512 CPUs. They've been running for over 100,000 time steps. That's a accrued over 1 million CPU hours. Luckily, we have grants and stuff. Thank you. So, and what does this get us? It gets us maybe a couple hours of convection. The simmering phase lasts for thousands of years. We are looking at just a tiny little snapshot into the span of this lifetime. Now, I've been talking about this 3D-ness, but I keep on showing these kind of boring 2D plots. So here's a 3D volume render of the convection zone. So this is kind of frozen in time, so nothing is moving. We're just spinning it around to show the kind of 3D-ness. I think it shows up better on that TV. Maybe. Whatever you want. So one of the key features of this convection is that it is kind of dipolar. And what I mean by that is that's why we have this separation of red and blue here. So the red regions, we colored them so it shows material that's kind of flowing away from the center. It's moving out. And these blue regions are the fluid flowing into the center. And these are very kind of distinct regions. So we're having kind of things moving out together, circling around and coming back in together. And so that's an interesting find that we didn't necessarily expect to see in these simulations. Okay, so just to recap a bit of the stuff I've just been talking about. So these are, again, simulations of a convecting white dwarf that we're kind of expecting to eventually heat up in thousands of years from now and explode into a type 1a supernova. We got to work in this kind of low Mach regime where things are just moving slowly. That can actually cause complications with the sort of fluid mechanics and physics of the situation. But we have our workarounds, even if we have to be extra careful about different perturbations or errors cropping up. And these are very expensive to make. So they make nice movies, but there's easier ways to make nice movies than this. All right, so why bother actually looking at this convection? Who really cares? So this is kind of where the science part of it all comes into play, where I'm going to be talking about the convective Urca process. So I'll have to introduce it first and then explain why it's important. So I promise you it is important. So we can split it up into convection and the Urca process. So I've been talking about convection a lot. It's kind of mixing materials. It's powered by the carbon burning in the core, all that good stuff. Now the Urca process is kind of a new thing. So this is a relationship between two nuclear reactions that pair kind of two different nuclei, two different isotopes. So this is an example of this kind of pairing where we have neon 23 and sodium 23. And these are the two reactions. You can see they're almost symmetrical. You get neon 23 is turning into sodium 23 and an electron. Then we have sodium 23 turning into neon 23, sodium 23 and an electron. And the only kind of difference between these two are these little neutrinos that get lost each time. So these neutrinos actually will take away energy from the star. They're just going to free stream away. And that can provide some cooling and maybe some other interesting effects that will affect this convection. Just some terminology, the sodium plus an electron, we call that an electron capture. It's taking in an electron, and the neon turning into sodium and electron, we call that a beta decay. So the neon's kind of decaying into the sodium, and we get an electron out of it. This is a nice infographic made from an REU student this summer, Kian Hayes. So we have our white dwarf here. In the center, it's burning carbon, it's convecting, and the kind of region where these reactions are important vary with the density of the star. So you can think of it as, for the electron capture, that's going to happen at the densest regions of the star, where these electron and these sodium ions are kind of smashing together and combining. But as we move further and further from the center, it's going to become less and less dense. And the sodium 23, or the neon 23 will be unstable, and there's going to be kind of room for the electron to dart out and run away from the atom. And so this means that there's kind of some sort of divide where these two reactions are equal and opposite, and we call that the Urca shell. So if you're kind of interior to the Urca shell, there's going to be a bunch of electron captures coming in. But if we move out from the Urca shell, we get lots of beta decays. And that's where convection kind of plays a role in this. It's able to transfer material in and out past this Urca shell and back and forth. And this process can kind of go on forever. These neons and sodiums, these kind of reactions are equal and opposite. Once you get into one, you get out of the other, right? And so this is never going to stop until, you know, the white dwarf explodes, but we don't worry about that. We can only simulate for about an hour. So I'm gonna show some of these movies again, just to explain a bit more detail. So what I've drawn here in this black line, that's the Urca shell itself. So, and the thing that we're actually plotting is the ratio between neon and sodium. So neon is what we expect to be largely in the center. That is the kind of product of those electron captures. And so we can see that's largely so, about 10 times as much neon as there is sodium in the center. But convection keeps on pushing this out past the Urca shell. And at first, nothing happens. The reaction rates are relatively slow. But as this material kind of circles back around, if it gets caught back up here, it's going to start kind of decaying into sodium 23. And so we're kind of watching this process of both convection pushing, moving material around, and the kind of aspects of the decaying that's going on at the same time. So what are some of the kind of consequences of this? This is looking at a plot of the energy generation. So it's kind of cleanly divided into 3 separate regions, which is very handy. We have the kind of interior where carbon burning, that's kind of driving the convection, and that's the most kind of dominant source of energy that we get out of all of this. But as we move out, it becomes we get to kind of a less hot, less dense region, and then we'll have all these kind of electron captures kind of dominating the energy. And these are actually losing some amount of energy. These are kind of endothermic reactions. As we move even further out, again, we see this kind of white ring, that's the Urca shell. And outside of that, that's the whole kind of decay region where we're again kind of letting loose energy. So this plot is showing kind of all of the nuclear energy generation. But if we add all of that up, we get this number about 2.85 times 10 to the 43 ergs per second. Ergs is a unit of energy that astronomers like to use because it sounds funny. And so we are generating energy. This number is positive. The white dwarf is kind of continually generating energy. That makes sense. It's heating up. It's on its way to exploding. Now, if we look at all of these kind of little neutrinos, we add all of those up and see how much energy is being lost by them. We have a pretty significant amount, 3.62 times 10 to the 42 ergs per second. But the kind of key thing here is that it's still less than the total energy being generated by the carbon burning and other reactions going on in here. So there had been some theories that when this IRCA process was initially proposed, that this could prevent the runaway, prevent the type 1 supernovae. That's kind of not been the standard theory for a while, and these simulations confirm that. So now I'm just kind of into some future work. Not sure how much time I'm supposed to take. Oh, I have more time. I'm gonna skip ahead. So I'm going to talk a little bit what the role of these simulations can kind of be in the picture of how do we blow up one of these white dwarfs, and what is the kind of right answer for the type 1a supernova things. So from just kind of a basic level, we can kind of inform theory or confirm different theories about what the convective IRCA process does. These simulations, the kind of computational power needed is pretty recent, but there's been lots of theories about how this convective IRCA process can affect the white dwarf during this sort of simmering phase. As I said before, we simulate an hour. These things last for thousands of years. So we really need these kind of one-dimensional stellar evolution codes that make a lot of approximations, but they can actually simulate the span of time, usually like on your laptop. So incorporating kind of the knowledge we gain from these simulations down into the sort of 1D stellar evolution codes, it's a pretty important piece and something to still kind of work on. And then finally, what we get out of those codes themselves is some sort of observational signature. We always have to wrap this back to actually looking up at the night sky, because that's what's real. Everything we do is just kind of a test bed of trying to figure out what might be the case, what might be working. And so we have to figure out what can our knowledge about this kind of simmering phase tell us about the supernova itself, and how we could maybe detect that the simmering phase is going on. And yeah, so we're still working on all of that, and we have different future ideas. So the IRCA pair that I've been showing, this neon and sodium, it's not the only one that exists in these white dwarfs. So there's always a possibility of including more like this fluorine and neon 21. And kind of looking at different temperatures and densities, because as I said, we looked at just a little sort of snapshot into the lifetime of the simmering phase. So we can look at different times in that kind of different snapshots, in particular, like closer to the supernova itself. What if we were days away from the supernova instead of years away? And maybe can we use these models as sort of an initial condition for one of those kind of explosion simulations that I showed before. So, final summary of everything that I talked about. I sort of told you how to blow up a star. There's still lots of missing pieces, but we're still working on it. Then hydrodynamic simulations. These can be lots of fun. They can be very cool videos, but there's lots of headaches and pains that we have to work through and be careful about, particularly when we're doing this sort of low Mach, slow moving fluid regime. And then convective IRCA, the sort of actual science part of all of this. All right, thank you guys so much for listening.
Great questions, I hope.
Yeah, if anyone has.
Yeah, ask a question about the finite volume method you are using. So you said for each cell you have its own properties like density, pressure, maybe Mach number and velocity. So how do we deal with the discrepancy of the boundaries?
That is a good question. So do you mean the boundaries for an individual cell or
Between
the
the cells, boundary between the two cells?
Yeah. So the boundary between the two cells, that's kind of where we use I kind of brushed over it, but the conservation laws, the like Euler equations, that tell us the sort of fluxes that go through the cells.
So between the boundaries, for example, there are two cells. On the left, it has some pressure is higher than the right side.
Yeah.
So there's a gap on the boundary. So how do we deal with this gap?
Well, there's no gaps in the boundaries.
So do you use, for example, use the interpolation?
This flow, these simulations, the boundaries are fixed. Mass and energy flows through them, so you calculate at the boundary. The calculation happens at the boundary.
Yeah, sorry, that's a better explanation. Thank you.
I work the other way around, so that's why I figured where his question was coming from.
I see. Thank you.
So a much more general question. Why do we need to work with volume and why can't we work with fixed mass? Like a finite element mass, like with mass staying fixed and volume varying, is that? Just curious.
I don't think I have a very good answer for you. I feel like
Oh wait, I think I realized why, because then they would move, the boundaries would move. That's actually
yeah,
a simple and
so
massive problem.
there are different kind of ways you can do this simulations and divide up your boundaries. And the reason why we do finite volume, I think it's primarily related to making sure the equations we follow conserve the mass, energy, and momentum above kind of anything else.
Yeah, because mass and momentum would not carry it. I do have another side question. So we are completely ignoring the speed of sound, right? More or less, because you're working low mark energy.
Yeah.
This is again more general. So can a pressure wave in the star be strong enough to cause fusion or anything?
Yeah, so I think the first movie that I showed, the kind of double detonation, that is the pressure wave compacting the core to ignite kind of secondary flame.
So can there be like, can that happen at smaller scale in the star anyway?
In a star like this with this kind of convection, I don't think there's going to be any sort of pressure wave that'll ignite that. One of the ideas for how we finally get from this kind of convection to a hot spot in the center will be through sort of turbulent mixing that can maybe concentrate a region of especially kind of hot material or reacting material to get to that sort of runaway. But from this setup, the pressure waves, I don't think so.
Why don't you show that movie again? And then there is something in the chat too.
Okay, so this very thing's kind of a pressure wave that's coming in. And we get that ignition there. And I read the chat question. It's the visualization of the NE/Na ratio flow looks really smooth. What's the resolution? So the resolution is 2.5 kilometers. Like the scales are about yeah, so the resolution's like 2.5 kilometers. And the sort of convection zone as a whole is around like 400 kilometers.
Yeah, I also have a question on this picture.
Yeah.
So the change of the color, I want to ask the main cause of the change of color is due to the physical movement of the elements waves or is due to the like chemical reactions, since you said that they can change into each other.
So it is kind of a combination. I would say primarily it's the motions themselves. The time scale for the motions are a bit faster. Yeah, it's primarily the motions that are causing this. The kind of reactions, I would say, are more of a kind of secondary effect that you can kind of see on the backside, where it's more purpley.
So I can understand that each time step is already a balanced reaction state, is it?
Yes, so yeah, the reactions, we split up the time step, we react for half a time step. Wait. Yeah, we react for half a time step, then we kind of modeled the motion for a full time step, and then react again for a second half of a time step. So then we kind of link the reactions to the motions themselves in this way. So they're kind of split, but split in the way that they still can kind of impact each other.
More general question. So in your sort of type 1A scenario, we just dump material to the star and you restart the fusion process. How does the subsequent evolution from that point to the supernova differ from the just normal type 2 supernova? Is it the exact same steps that you go through, or?
No, these are pretty different, because I think for type 2, it's kind of a collapsing of material coming down. And there's no really collapsing of material in that sense. We're starting, so the white dwarf is gaining material through kind of some accretion disk, but it's not a full collapse that's causing this explosion. It's more kind of a slow buildup of temperature and fusion that eventually runs away into an explosion. So it starts, we have some sort of flame that starts in the middle and that expands out.
So you don't go through like all the burning steps to iron and then moving on to neutron star and all that stuff.
Oh, I see. So there are more steps to the flame, but this won't ever go into a neutron star or anything like that. These the supernova is going to kind of incinerate the white dwarf, is the understanding that we have. So there should be kind of nothing left behind. Other questions?
So like in this simulation, does it look like the why is it like asymmetrical, like goes one side?
That is a great question. So this all has to do primarily with the convection, the shape of the convection itself. I think it's easiest to see. So here I drew some streamlines. I guess this is flipped, but the general kind of flow of material is upward. And in this core region, this is where we have lots of this kind of neon. Yeah, so that's why it's kind of the most white, brightest. And so that the convection is pushing all of that material up essentially. And we get this sort of asymmetric shape because it's taking material from the inside, pushing it up. And it doesn't have time to react and change into the sodium-23 and turn purple until it kind of circles around to this backside where it's kind of can stay out in the outer regions where it can actually react and change.
So there's a flow happening, and this flow for a more realistic start would be anyway. This up is not exactly the thing.
Yeah,
right?
I chose up because I liked it.
Makes sense.
Yeah.
Okay.
So just to be clear, this is a slice of a 3D simulation domain?
Yes, yeah, this is a slice I can. this is the volume render. It's should be kind of showing a similar thing where things are moving up, circling around. You can see that if we like took a slice, then we get this kind of round structure. You can see the round structure. Yep.
The boundary is the whole star, not the Urca shell?
Oh, no, this is the Urca shell. I don't think I ever actually said that. Yeah, this white region is the Urca shell. You can see. So the regions are colored just at a kind of specific velocity. So you don't see quite as much of it expanding across the Urca shell, but there still reaches, especially like up here, I think. Expands, yeah. Good question, yes.
I was curious about the computing resources. I think you said like you're using CPUs. I was wondering if this, like if it would be straightforward enough to use like GPUs to accelerate some of the simulations, or if that's something you try.
Yeah, so it should be easy. And I did try, and I got lost and confused a little bit. So as I said, the kind of AMRX framework has that kind of capabilities built in. And so it'll just take me taking some time to figure out different pieces in the Maestro X code that need to be altered so that we can put it all on a GPU. There's other codes, some of the simulations that I showed that Eric over there works on. They use GPUs and do everything on a GPU basically. And it does speed things up, so.
Yeah.
It runs hundreds of times faster on GPU.
Nothing big. Another thing to add to future work. Yes. Thank you guys so much for listening. And